Hi, welcome to Mean and Standard Deviation of the Binomial Distribution, the sequel. In this video, we'll derive the mean and standard deviation of the binomial distribution. We already did this once in the video Mean and Standard Deviation of the Binomial Distribution. Here we'll get the same results, but use a different method. One reason to do this is that it's generally useful to know more than one way to derive important results. But there's also another reason to derive these results again. The binomial distribution is closely related to the Poisson distribution. We derived the mean and standard deviation of that distribution in the video Mean and Standard Deviation of the Poisson distribution. But we used methods that were rather different than those which we used for the binomial distribution. So here we'll use methods similar to those in Mean and Standard Deviation of the Poisson distribution to re-derive the mean and standard deviation of the binomial distribution that we got before. This will hopefully bridge a gap between the two previous videos. So this video will assume you're familiar with the binomial distribution at the level it is covered in the videos the binomial distribution and why the binomial distribution is important, available on this channel. You'll also need to know what a mean, or average, a variance, and a standard deviation are. If you don't, you can find them in mean, median, mode, variance, and standard deviation, also available on this channel. It might help if you've already watched Mean and Standard Deviation of the Binomial Distribution, but that video isn't strictly necessary. Alternatively, you might want to watch that video after this one. You also don't need Mean and Standard Deviation of the Poisson distribution, but we'll go through very similar steps here, so watching that video first might make following this one a bit easier. Okay, let's get started. Okay, first let's quickly remind ourselves what the binomial distribution is. We take a coin that has a probability pH of coming up heads and a probability pt, which is equal to 1 minus pH, of coming up tails. We flip the coin n times. The flips are all independent of each other. The probability p of m, given pH and n, for the coin to come up heads m times and tails n minus m times is the binomial distribution. So p of m, given pH and n, is equal to pH raised to the m power times 1 minus pH raised to the n minus m power times n factorial over m factorial n minus m factorial. Our goal here is to obtain the mean and standard deviation of this distribution. As a first step, let's see what happens when we sum this expression over m. So, p of m, given pH and n, is the probability that in n flips of a coin, it will come up heads m times. If we flip the coin n times, it may come up heads 0 times, or 1 time, or 2 times, etc., up to a maximum of n times. In other words, m must take on some integer value between 0 and n. If we add up the probabilities for each of these possibilities, they must sum to 1. So we have that 1 equals the sum from m equals 0 to n of p of m given ph and n, which means 1 equals the sum of m from 0 to n, ph raised to the power of m, 1 minus ph raised to the power of n minus m, times n factorial over m factorial n minus m factorial. We'll use this relation to get the mean and standard deviation of the binomial distribution. Okay, so we'll start with the mean of m, which we write as m in angle brackets. We will eventually obtain the perhaps unsurprising result that the mean of m is equal to nph. The procedure we'll go through to get this result will be a bit involved, but will serve as a good warm-up exercise for obtaining the standard deviation sigma m. First, let's remind ourselves what the mean of m is. So let's flip the coin n times. Note how many times m, between 0 and n, it comes up heads, and then repeat the whole process many times. Let's call each set of n flips a trial. We'll conduct t trials and label which trial we're talking about by the index little t. And we should note that in the video Why the Binomial Distribution is Important, we used the word trial to mean a single flip. Here we're using it to mean a set of n flips. Okay, let's call the value of m for the tth trial mt. We want the mean value of m observed over the t trials. So the mean value of m is equal to 1 over t times the sum over the trials of mt. We'll take the number of trials t to be very, very large. For some of these trials, or in other words, for some values of little t, mt will equal 0. For some, mt will equal 1. For some, mt will equal 2 or 3, etc., up until mt equals n. Okay, let's group the t trials according to the value of mt for that particular trial. So we have that the mean value of m is equal to 1 over t times the sum over the trials of mt. We now rewrite that as 1 over t times a series of sums. The first sum is the sum over all trials of mt, but only including those trials where mt was equal to 0. The second term is the sum over all trials of mt, but only where mt was equal to 1, and so on. So this latter form contains n sums. Now each sum in the new expression is still over the t trials, but we put only the trials with mt equal to 0 in the first sum, only the trials with mt equals to 1 in the second sum, etc. The trials with mt equal to n are in the last sum. Okay, so let's see how many terms each sum in our new expression contains. So let's start with the first sum. This sums mt for all trials in which mt is equal to 0. So how many such trials are there with mt equal to 0? We take t to be very large, so the number of trials which have mt equal to 0 will be very close to t times the probability for a given trial to have mt equal to 0. Now, the probability for the tth trial to have mt equals 0 is just given by the binomial distribution evaluated for m equals 0. So p of 0 given ph and n. So for t very large, the number of trials with mt equal to 0 will be very close to t times p of 0 given ph and n. Similarly, the number of trials with mt equal to 1 will be very close to t times p of 1 given ph and n. The number of trials with mt equal to 2 will be very close to t times p of 2 given ph and n, etc. So we can rewrite our expression for the average value of m as 1 over t times t times p of 0 given ph and n times 0 plus t times p of 1 given ph and n times 1, etc. Okay, so canceling the factors of t, we can rewrite our previous expression for the mean of m as the sum over m from m equals 0 to n of p of m given ph and n times m. And that's equal to the sum over m from m equals 0 to n of ph raised to the m power times 1 minus ph raised to the n minus m power times n factorial over m factorial n minus m factorial times m. Now we have to figure out how to do this sum. Okay, so this sum from the previous slide looks a lot like the sum we said earlier was equal to 1. So we had said that 1 is equal to the sum from m equals 0 to n of p of m given ph and n, which is the same expression as we have at the top of the slide, except it doesn't have that final factor of m at the end. So these two expressions are not exactly the same. The expression that we want to calculate has an extra factor of m. Okay, so let's see if we can rearrange our expression for the mean value of m into a form where we can use that handy sum from earlier. So first, let's note that the m equals 0 term in the sum is equal to 0. Remember that 0 factorial is equal to 1. So we can start the sum from m equals 1 instead of m equals 0. So here we rewrite our expression for the mean value of m, except that now the sum goes over m from 1 to n instead of from 0 to n. Next, let's note that m over m factorial is equal to 1 over m minus 1 factorial. And let's also move a factor of ph and a factor of n out front. So we had our previous expression for the mean value of m, which was the sum over m from 1 to n of ph raised to the m power 1 minus ph raised to the n minus m power times n factorial over m factorial n minus m factorial times m. Now we're going to write that as phn times the sum over m from 1 to n of ph raised to the m minus 1 power times 1 minus ph raised to the n minus m power times n minus 1 factorial over m minus 1 factorial n minus m factorial. Okay, so now let's note that n minus m is equal to n minus 1 minus m minus 1. And what we're going to do now is take our previous expression and just replace the n minus m in the exponent on the 1 minus ph, and we're going to replace that with n minus 1 minus m minus 1. And we're going to take the n minus m factorial in the denominator, and we're going to replace that with n minus 1 minus m minus 1 factorial. Okay, so let's define m prime to equal m minus 1 and rewrite our expression in terms of m prime. The sum in m from 1 to n becomes a sum in m prime from 0 to n minus 1. And while we're at it, let's define n prime to equal n minus 1. So now the sum is going to run from 0 to n prime. So we put those substitutions in our previous expression, and we get that the mean value of m is equal to ph times n times the sum over m prime from m prime equals 0 to n prime of ph raised to the m prime power 1 minus ph raised to the power of n prime minus m prime times n prime factorial over m prime factorial n prime minus m prime factorial. Okay, so we have our relation from the previous slide. Let's compare this with the relation we had before, which was that 1 is equal to the sum over m from 0 to n of p of m given ph and n, which is written out here. If we look closely, we'll see that the two sums are the same except for the primes on m and n. Now, this relation holds for any n, so the prime on n prime doesn't matter. And whether this quantity we sum over is called m or m prime, the sum is the same. So the sum in our expression for the mean value of m is just equal to 1. So we had that the mean value of m was equal to ph times n times this sum that's just equal to 1. We thus get that the mean value of m is equal to phn as expected. Okay, now that we've gotten that the mean value of m is equal to ph times n, let's move on to the standard deviation of m, sigma m. To get sigma m, we'll first get the variance of m, and then we'll use the relation that sigma m is equal to the square root of the variance of m. Now, let's note that the variance of m is the square of mt minus the mean value of m averaged over the t trials. We can write this as the square of mt minus the mean value of m, all in angle brackets. Okay, so just as with the mean value of m, we could break the sum over trials in the variance of m into n sums, putting the trials with mt equals to 0 in the first sum, those with mt equal to 1 in the second sum, etc. We'll skip the steps this time, but the procedure yields the following. We transform our original expression for the variance of m, which is 1 over t times the sum over trials of the square of mt minus the mean value of m, into a sum over m from m equals 0 to n of p of m given ph and n times the square of m minus the mean value of m. Okay, so we have that relation from the previous slide. Now, the quantity that we're taking the average of is the square of m minus the mean value of m, which is equal to m squared minus 2m, the mean value of m, plus the mean value of m squared, which equals m squared minus 2m phn plus phn squared. Okay, so the average of the sum of the three terms in our expression is the sum of their averages. So the average of the square of m minus the mean value of m is equal to the mean of m squared minus the mean of 2m phn plus the mean of phn squared. Now, the mean value of m is phn, and phn is just a number, so the mean value of the square of m minus the mean value of m is equal to the mean of m squared minus phn squared. This means that we need to calculate the mean value of m squared. However, in order to calculate the mean value of m squared, it will be easier to first get the mean value of m times m minus 1. So let's do that. So the mean value of m times m minus 1 is equal to the sum over m from 0 to n of p of m given ph and n times m minus 1. And that equals the sum over m from 0 to n of ph raised to the power of m, 1 minus ph raised to the power of n minus m, times n factorial over m factorial n minus m factorial times m minus 1. So first, the m equals 0 and m equal 1 terms are 0. So we can start the sum from m equals 2. And also we can use the fact that m times m minus 1 over m factorial is equal to 1 over m minus 2 factorial. Okay, so we take our previous expression for the mean value of m times m minus 1, and we take the factors of m minus 1 in the expression and cancel them with factors in m factorial in the denominator. That gives us m minus 2 factorial in the denominator, and instead of taking the sum from m equals 0 to n, now we take it from m equals 2 to n. Okay, next let's move factors of n times n minus 1 and ph squared out front. So now we have that the mean value of m minus 1, is equal to ph squared n times n minus 1 times the sum from m equals 2 to n of ph raised to the m minus 2 power, 1 minus ph raised to the n minus m power, n minus 2 factorial over m minus 2 factorial, n minus m factorial. Okay, so we have our expression from the previous slide. Now let's rewrite this in terms of m prime, which we define to be m minus 2, and n prime, which we define to be n minus 2, noting that n minus m is equal to n prime minus m prime. And we get that the mean value of m times m minus 1 is equal to ph squared n times n minus 1 times the sum over m prime from 0 to n prime, ph raised to the m prime power, times 1 minus ph raised to the n prime minus m prime power, times n prime factorial over m prime factorial n prime minus m prime factorial. Okay, so we have our expression for the mean value of m times m minus 1 from the previous slide. Now if we look closely, we can see that the sum in this expression is the same one we encountered before, which was equal to 1. So the mean value of m times m minus 1 is equal to ph squared n minus 1. And we can also see that the mean value of m squared is equal to the mean value of m times m minus 1 plus the mean value of m. So that means that the mean value of m squared is equal to ph squared n minus 1 plus ph n. Okay, so we have that the mean value of m squared is equal to ph squared n minus 1 plus phn. We said earlier that the variance of m was equal to the mean value of m squared minus phn squared. So the variance of m is equal to ph squared n times n minus 1 plus phn minus phn squared, which equals phn minus ph squared n, which equals phn 1 minus ph. Okay, so sigma m is equal to the variance of m taken to the 1/2 power, so sigma m is simply equal to the square root of n ph 1 minus ph. Okay, so let's summarize. Here we've re-derived through different methods the same results for the mean and standard deviation of the binomial distribution that we saw in the video mean and standard deviation of the binomial distribution. The results that we got there and here are that the mean value of m is equal to nph, and sigma m, the standard deviation of m, is equal to the square root of n ph 1 minus ph.